Hello and welcome to another continuation of an existing episode of How to Understand X. Yesterday I worked on that 4.5 hours of what's it called? Derivative practice, but I very quickly realized that I was extremely tired, so I just went to sleep. But, we're here today. We finished 3 hours yesterday, so we're gonna finish 1.5 hours today. And I found out about some things that I forgot to mention, and that being optimization. Optimization works a lot like related rates, as we tackled yesterday, but we're just going to have to go through it a little bit right now. So our first problem, I'm just going to start with an example. Usually I'd like to say what is happening and then do an example, but I think for these kinds of problems it's better if we just go straight to the example. The product of two positive numbers, I'll just say 2 n in n, right? The product of two positive numbers is 363, and then minimize the sum of the first and 3 times the second. Okay, well, we have a lot going on right now, but let's just talk about the product of two numbers, positive numbers, that with a product of 363. So let's say that our first number will be x, and our second number will be y. xy equals 363, and we have to minimize the sum of the first, so x, and 3y. Alright, excuse me, no, you get it. 3 times the second number, which is 3y. And we have to minimize this. Alright, so how can we do this? First step is we have to express x plus 3y in terms of one variable. It could be either x or y, but since we are more used to taking the derivative with respect to y, with respect to x of y, I think we should express this in terms of y. So we can say, after we divide both sides by x, we can say that this is x, we'd have y is equal to, these will cancel, 363 over x, or 363 times x to the negative 1. So from here, let's multiply 3 times 363. So what would that be? That would be like 1089, I think. 1089 over x. And this is what we are attempting to minimize, right? So we can call this a function of x. We do have two inputs, or two places where we can input values, and both of those places are inputs of x. So this is a function of x. And now from here, we can take the derivative of this. We are trying to minimize, right? So if we take the derivative, and we see when this derivative is negative, or not when it's negative, but when this derivative is equal to 0, we will have a horizontal tangent, and then after that, we can see if it's concave up or concave down, and see if we have a minimum or a maximum. So let's set this equal to, let's do the derivative first. We have f prime x, and I'll write this as a x plus 1089 times x to the negative 1. Because, it'll be easier to differentiate that way. Derivative of a x, we said that was 1, minus 1089 over times x to the negative 2. All right, we bring that negative 1 out, and then minus 1, we get minus 2. So we have, this is 1 minus 1089 x squared, and this has to equal 0. Right? We're trying to say that if this is a function, the horizontal tangent, if that equals 0, we get either a minimum, a maximum, or neither. So we want to see if there's any minimums, which is what we can get, because we expressed this term, what we are trying to minimize, as a function of x based on the other formula we got, xy equals 363. So if we made all of that a function of x and we did the derivative, then we can find the relative minimum of the graph if it was expressed as a function of x. So let's do 1 minus 1089x squared equals 0. I'm not sure if this will be the best first example, but we want to set our derivative equal to 0. The pattern is what you need to notice. And so we will subtract both sides by 1, or you could actually think of it as adding 1089 over x squared to both sides. So you get 1089 over x squared is equal to 1. So if you multiply that x squared to that, you will get x squared equals 1089, which means that x is equal to plus or minus square root of 1089, which I need to use a calculator for. Let me get this out. No, it's a really nice 33. I mean, I probably could have, gotten somewhere in that ballpark, but it's nice that we don't have to. So we have 33 so we get x equals plus or minus 33. So let's review what that meant. We have, we will eliminate one of those plus or minus 33s, but we had a function. We had the product of two numbers, and we expressed one of those numbers as a function of another number. And then whatever we're trying to minimize or maximize, we make everything as a function of one variable, usually x. Then you do the derivative, and then you try and find if there is a maximum or a minimum at a specific point. Now, we could do x equals negative 33 and find some stuff, but x equals negative 33 is not allowed. We have the product of two positive numbers, right? So x has to equal 33, and let's just cross our fingers and hope that this is a positive number when we plug it into our second derivative. So we have a horizontal tangent, right? We know that there is a horizontal tangent when x equals 33. Okay, let's keep going. We know that there is a horizontal tangent when x equals 33, so now we have to do f double prime of x, right? We don't know if this is a minimum or a maximum or neither, so we have to do the second derivative test. So derivative of a constant 0, we bring that negative 2 out there. We will have, this is getting a little bit difficult for me, let's say 178, so 2,178 times x to the negative 3. Okay? And I could, calculate this, but I wouldn't say I'm lazy. I'm just, working smarter, not harder here. We know that if we have a horizontal tangent at x equals 33, that if the second derivative is positive, or if we have a concave up, and we know that there is a horizontal tangent on this concave up, then it has to be the relative minimum. And, likewise goes opposite. If we know that there is a horizontal tangent and the graph is concave down, which of these points have a horizontal tangent? It's going to be the maximum. Okay, so we have to see if when you plug in x equals 33, this is a positive or negative value. And 33 to the power of negative 3 is a positive value. It's 1 over 33 cubed, right? And this is a positive number times 2,178, which is also a positive number, is a positive number. So we will have f double prime of 33 equals, let's write down what we know. We have f prime 33 equals 0, and f double prime of 33 is greater than 0. That means that we have a relative minimum at that x value. And now, once we know that x equals 33 is the x value of the minimum, we have to plug it back into f of x, right? The function that we originally had. So let's write that down. Well, we could actually, no, we can't plug that back into xy. We can just do this correctly. We'd have x plus 1089 over x is, so this is 3y, right? If y is equal to 363 over x, because xy equals 363. So to plug in this, you get 33 plus 1089, so 33 squared over 33, which is going to just be 33. So we're going to have 66. And that is the smallest possible sum of the first and second number of two numbers that multiply to 363. I'm hoping you see the logical leaps that we've made so far. We have a function, or we have some type of expression. The first function that we got was product. So we express the product in terms of one variable, so that when we differentiate, we can only differentiate to one variable. Because if we did some crazy attempt to try and differentiate two variables at the same time, it would be much, much more difficult to calculate. So we try to express one variable in terms of another, and then depending on what we are trying to minimize or maximize, we take the derivative of this function, this new function of whatever we're trying to minimize or maximize. So we take the derivative of that, and then wherever that derivative equals 0, we do the second derivative test. If a graph is concave up, and we have a horizontal tangent, the only horizontal tangent will be at that relative minimum. And if we have a concave down, we will have a relative maximum. And again, we can really quickly go over what y concave up is concave up and y concave down is concave down. We said last video that if the derivative is greater than 0, then f is increasing. So if the second derivative is greater than 0, that means that f prime is increasing. And if you were to draw a graph where f prime, or the slope of the tangent line, is constantly increasing, if we start off at very negative, and then slowly but surely, we do get less and less negative, right? We start off very negative, slightly less negative, even less negative, 0, and then we start actively increasing, right? The slopes of these tangent lines, we can even try and draw. These are shooting outwards, right? The slopes of these tangent lines are increasing. And same thing goes for concave down. And concave down, we can say that if you have this graph of f prime, and as the slopes of the tangent lines at each of those points goes along, so we can try even drawing the full lines to really illustrate it. It starts off, we have a horizontal line. I can draw a straight line, and then, goes down. But as you can see, it starts off extremely positive, slightly less positive, till you get to even 0. Then it'll become negative, more negative, and extremely negative. That's concave down and concave up, and why they look like the way they look. And so you can use the second derivative test, or if you find that the first derivative is equal to 0, the second derivative test says that if it's greater than 0, the second derivative, then your point, your horizontal tangent, will be a relative minimum. And if you have a second derivative that is less than 0, you have a relative maximum. So, yeah, let's do some more optimization problems to really try and get what's happening. So, we have right now the sum of the first number and the second number, or twice the second number, is equal to 100. And the product is a maximum. So we have to maximize xy, right? So let's try and express this function as a function of one variable. So we can bring that x to the other side. So we can subtract x from both sides perhaps. Negative x, negative x. So we'll have 2y is equal to 100 minus x. So we can write this as y is equal to 100 over 2, so 50 minus x over 2, so 1/2 x. And now we are attempting to maximize xy. So we can say this is x times 50 minus 1 half x, and so we have negative 1 half x squared plus 50x. And now some of the more savvy might know that this will be a negative parabola, right? Because we have a quadratic, we have x squared, so this will be a parabola, and we have a minus in front of that 1 half. So it will automatically look like that. And you know, you could do axis of symmetry, say x equals negative b over 2a, and work from there. And you know, you'd probably, not probably, you will get the same answer. But we are working with derivatives, so we want to be consistent. If this is f of x, what would be the derivative? Now the derivative, we have n equals 2, so we can bring that out. 2 times 1 half is 1, so we'll have negative 1 times x to the 2 minus 1, so 1. So that will just be negative x, and then derivative of x is just going to be 1, so we have negative x plus 50. We set that equal to 0, you can add x to the other side, and you will get x equals 50. That will be the x value at which f prime is greater, or when the derivative is equal to 0. And now, since you know that the graph looks like this, you can just assume that, hey, the only horizontal tangent is at the vertex of this parabola. But, you know, we want to be consistent again, so we will do the second derivative test to really make sure. But this is a nice and easy one. We said that the derivative of x is just going to be 1, so f double prime of x will just be negative 1. And regardless of what input 50, or regardless of what input x is, if it's 50, if it's a million, f double prime is negative 1, which means that f double prime is less than 0, so the graph is concave down, which means that the only horizontal tangent will be the relative maximum, which means that x equals 50 is going to be the x value of the maximum product, but we do need to solve for y. So if y is equal to 50 minus 1 half x, then 1 half times 50, let's scratch out the x, 1 half times 50 will be 25, right? So y will equal 25. And now when we multiply these two, we will get, I think, just 1250. Yeah, so xy, or what we are attempting to maximize, will be 1250. It'll be, you can even write this back into here as this f of x. If you plug in 50 into here, you'll get like 2500, or not 2500, wait, what? Oh, no, yeah, you get 2500, but you have to divide that by 2, so that'll be 1250 plus 50 times 50, which is again 2500, so 1250, negative 1250 plus 2500 is positive 1250. But again, you can just write this as xy. So yeah, I'm hoping you see those connections. These two have been, well, the second one is a little bit easier than the first, but again, we just have to find some relationship between two variables, express one variable in terms of another, and then differentiate with respect to that variable, and then do the first derivative and second derivative test to try and maximize or minimize whatever we're trying to do, or optimize our solution. So let's do another one. This will be another common type of question that you will see. You will have the length and width of a rectangle. So let's draw that. Length and width of a rectangle has a perimeter of, we'll say that this length is y. I mean, this length is x, and the width, wait, I don't know. Let's say x is length and y is width, or whatever, and then we have a perimeter, so 2x. We just have to sum up all these sides. 2x plus 2y is equal to 100. And we have to maximize area. Again, xy, base times height, or length times width, or whatever. And so let's express 2x plus 2y in terms of x. Wait. Oh no, I thought this was the exact same as the other question, but we're using 2x instead of 2y. Again, this is relatively simple, but, you know, never hurts to practice. We can divide all of this by 2, right? We have even numbers as coefficients, so we can have x plus y is equal to 50, which means that, or do I want to do that? Yeah, we can. And then we have y will equal 50 minus x. So we can plug this back into xy. We'll have x times 50 minus x. So we'll have 50x minus x squared. When you distribute that x to both these terms, and then if this is f of x, f prime x, we said derivative of x is going to be 1, so we'll have 50 minus, we can bring that 2 out, 50 minus 2 times x to the 2 minus 1, so x to the 1. And now we can set this equal to 0, and you can do the math for this. We can at least show a little bit of it. You bring that 2x to the other side, so you have 2x equals 50, which means that x equals 25 when you divide both sides by 2. And then if x equals 25 and y equals 50 minus x, y will equal 25, right? 50 minus 25. And so our, maximum area will be, oh, wait, almost forgot to do our second derivative test because we're trying to stay consistent. Sorry. I've just seen a couple of these problems too many times. We have to do the second derivative test to know for sure if this is a relative maximum or not. So we'll have f double prime of x, and then derivative of x is 1, and then derivative of a constant 50 will be 0. So we'll have negative 2, right? 1 times negative 2. And regardless of whatever x is, this will always be negative 2. So f double prime is always going to be less than 0, which means that we have a concave down, and if we have a horizontal tangent, that horizontal tangent will be a relative max. So with that, let's plug back. We said that y was equal to 50 minus x, and then we plugged x equals 25 to get y equals 25. So we have xy, and we need to calculate that. We have 25 times 25, which is going to be 625, right? I'm hoping I'm not embarrassing myself. It might be, wait, let's see. It's just, wait. No, it is. Is it? I feel like I'm losing it. Okay. So, 400. No, we're good. Good. So, whenever you have multiples of 25, you can just express the second number in terms of 4. So, that's how I calculate or recheck my work. But, 25, if you divide that by 4, you'll have 6R1. So you have 600 times 1 times 25. So 625. That's like a fun trick, I guess. That's because, 25 times 4 is equal to 100. So if you have a bunch of multiples of 4, if you just divide the number, like 25 times 25, by 4, if you divide the second number by 4, then you will have 6 times 4, so 25 times 6 times 4, and then times 1. So this 25 times 4 we said was 100. 6 times 100 is 600. And then this is added to 1 times 25. So 625. Yeah, it's just a nice little trick to use. And then we can start one other problem. And we have a word problem. So when you're given exactly what you need to use, it might seem a little bit easy, but word problems can be rather tricky. So let's attempt to do so. We have the management of a large store wishes to add a fenced-in rectangular storage yard of 20,000 square feet, using the building as one side of the yard. Find the minimum amount of fencing that must be used to enclose the remaining 3 sides of the yard. So we have 20,000 square feet, right? This is the area that they are trying to enclose. This is the storage yards. They didn't explicitly say area, but they said they want to add a fenced-in rectangular storage yard of 20,000 square feet. So this xy will equal 20,000. And then let's try and draw a diagram. Let's say that this is one side of the building. That's a straight line. And then let's say we have this fence around it. This area is 20,000. and not 200,000, 20,000. And we have x, and then y, right? And you might think, oh, there's another y, this is a rectangle. But we're already using one part of the building. We don't have to add in a fence. If you just think about this in terms of real life, you don't have to add a fence where a building already exists. So that's something that you need to recognize in these kinds of problems. You need to see exactly what is being asked. And I mean, they did tell us, find the minimum amount of fencing that must be used to enclose the remaining 3 sides of the yard. So they did kind of, nudge, nudge, wink, wink, tell us that there was only going to be 3 sides. But in slightly more difficult contexts, you will not be told. You just have to either draw a diagram and see, or just kind of know. So let's express this xy in terms of x, or express this variable in terms of 1. So we have, or one variable. So we have 20,000 over x when you divide both sides by x. Right? And then we are trying to minimize this right here. We have 2x plus y, and we are trying to minimize this. So this is equal to 2x plus 20,000 over x. This is going to be our f of x. This is our f of x. And so let's do a, no, f prime x. We have to do f prime x. This is our f of x, so f prime x, we can express this as 20,000 times x to the negative 1. Right, you might be, I know it's a little bit confusing, but the derivative of ln x is 1 over x, but the derivative of 1 over x is very, very different. So the derivative of x, we said, was 1, so we have 2 times 1, which is 2, plus, we can bring that negative out. We have minus, or plus negative, so minus 20,000 times x to the minus 1, so x to the negative 2, which we can write down here, x squared. Okay, and we have to set this equal to 0. So we can erase this. We know what xy is equal to. So we have 20,000 over x squared is equal to, 2 minus this, but we can just add this 20,000 x squared to the other side. So we'll have 20,000 x squared equals 2. And then from here, we'll have x squared equals, well, I won't spoil it. We can do both of the steps. We'll have 2x squared. We multiply this side to the other, equals 20,000, which means that x squared equals 10,000, which means that x will equal plus or minus 100. And again, we could plug in negative 100 and see what this would be, but x cannot be a negative number. You can't have a negative length of some type of fence, right? So let's erase this. So with that, x equals 100. That's right, x equals 100. We have, we can plug that back into f of x. We would have 2 times 100 plus 20,000 over 100, which means that we have 200 plus, these two cancel out, 200, so we have 400. That is the maximum, or, wait, totally forgot something. Forgot to do the second derivative test. 1 second. Okay, I'm bad at this, alright? Give me a chance. We have f double prime of x. We can make this back into 20,000 x to the negative 2. So, and then negative, and then derivative of a constant 0, and if you bring that 2 out front, or negative 2 out front, you'll get positive 2 times 20,000 would be 40,000, and then x to the negative 3, so we can bring that back down. And again, we are not going to be working with negative numbers because we can't have a negative, we can't have a negative fence, right? So from here, we plug in, we have our 100, and I don't want to calculate all that, but all we need to do is just say that if we were to plug in a positive number into here, all of this would be positive, which means that f double prime would be greater than 0, so we have a concave up function. And if we have a horizontal tangent, so concave up, horizontal tangent, that means that we have a minimum. And I actually kind of already did the work, but x equals 100 is our value, so we have 2 times 100, which is 200, plus 20,000 over 100, which is also 200. So we get 400 is the minimum of that function. And let's continue onwards. We have we have some interesting ones actually. So we have a person has 400 feet of fencing to enclose 2 adjacent rectangular regions. So 2 adjacent rectangular regions of the same size. What dimension should each region be so that the enclosed area will be a maximum? So we're going to have x, y, right? We have 2 rectangles of the same size, so x, and then y, we'll let that be y, x. Okay? And let's see. Should we... It just says 400 feet to enclose this, just to enclose this, not to actually surround both of these. So I'm going to assume, again, it's a little bit vague, but I'm going to assume that we have 4x plus 2y is equal to 400. So I'm going to divide everything by 2. So we have 2x plus y is equal to 200, which means that y is equal to 200 minus 2x. Okay, and we have an area 2xy, so we have 2xy, so we can write this as 2x, 200 minus 2x, and then we have 400x minus 4x squared. That's going to be f of x, which means that when we take the derivative of x is going to be 1, so we have f prime x is equal to 400, and then you can bring that 2 out, times 4, we'll have negative 8 to the times x to the 2 minus 1, so x. And then this is equal to 0. Add that 8x to the other side, so you have 8x equals 400, and then divide both sides by 8, you'll get x equals 50. And now we can do the second derivative, f double prime of x. We said the derivative of a constant is 0, and derivative of x is going to be 1. So we have negative 8 times 1, so negative 8, which means that regardless of what x is, the second derivative will always be less than 0, which means that the graph is concave down, which means that we have a relative max. And we were supposed to maximize that area. I'm not sure if I mentioned that at the beginning, but yes, x equals 50 does fall into this. So now we can plug x equals 50 back into our equation. So right here we have x equals 50, so 50 times 2 will be 100, and then 200 minus 100 is going to be 100. So we have y equals 100, which means that 2xy will be 2 times 50 times 100. Alright, and that means that we have 100 times 100, which is going to be 1,000. Yeah, I think that makes sense. Let's see if that makes sense. So this will be 100. This bottom right there, and then y is also equal to, so it's a square. Oh, it's a square, and then the perimeter will be 4 times. So that makes sense, I think. There is like a bit of a cheat to this, but I don't want to tell it to you. Just think about we're working with a lot of vertices. I think I might have actually mentioned it, but we're working with quadratic equations most of the time. And if you are asked for a minimum or a maximum, there is a rather easy way to find one. But, you know, we shouldn't do that because we're calculus students, not algebra students. So, our next question is: an open box is to be made from a square piece of material, uh, 12 inches on each side, 12 inches on each side, by cutting equal squares from each corner. So, equal squares, and then turning up the side. So, let's imagine this. If you have some kind of a shape like that, we can kind of think of this as a box, right? If you, I'll try drawing it. We'll have an open box, right? So let's kind of erase these lines a bit, make them somewhat separate, just to show that this is that's not what I wanted to do. But this top is not there. But if you fold these sides down, they will fall flat, right? They will go outwards. So let's erase these circles. If you were to, fold that flap down, you'd have a flap down here. And if you were to if you were to fold this flap down, you'd have a flap down here, and then this flap you'd go out there. Same over here. And these are all squares of empty space of equal length. And the question is, find the volume of the largest box that can be made in this manner. So we have not too much information, but we can come up with some information. So let's say that the side length of one of these squares is x. So we're going to have x, x, and then 12, and then x, x, and then 12, x, x. We're just labeling what the, and 12 is all of this, right? All of this is 12, x. Which means that the length of one of these is going to be 12 minus 2x, right? And then from here, let's see what we can do. Let's go back to that drawing. If we were to, say, draw that box again, right? We have this open-faced box, and when we did that flaps out, it would look like that, right? If we were to do the flaps out, we'd have a shape like that. So if we were to, I'll just draw an arrow to show that we flip them down, right? Now to kind of imagine what the height of this box is, because we're trying to calculate volume, right? The height of this box, if this is the flap, if you just go back there, you'd see that the flap is still x. This is the height of this box, which means that the volume is going to be 12 minus 2x times x. Okay? So, yeah, I'm hoping that you can kind of see it, and this seems a little bit redundant or unnecessary, because redundant or unnecessary is where we want to, live, because that just shows that you understand what you're doing. But let's go back. We have this, box, and when you pull those flaps down, we said that it would look like that, right? So this is going to be equal to that, right? This is just the same box side, just flip downward. So this x, this empty space, because this is like the empty space that we're talking about, this would be x if this was some type of a cube. This x is going to be the height of our box. So this is what we're going to calculate volume with. We have 12 minus 2x. That is one side. So we can think of that as this. And then we have well, we have to do something else times this, but we have this, right? And 12 minus 2x, 12 minus 2x, and then we have the rest of our box. So from here, we said that the height was going to be x, which means that the entire function for all of this is going to be x times 12 minus 2x squared, right? And this makes sense if we draw like some dashed lines to represent the base of the square. The length of those sides will be 12 minus 2x. So something to think about. Now let's actually try and minimize this, or maximize this volume. Sorry. So we have, we can, actually do this and then distribute it, but I think it's fun to use product rule because it's been a little while. We have f of x equals that, which means that f prime x. Oh, and we're going to use chain rule too, so that's fun. There's the derivative of this times that plus the plus that times the derivative of this. So we're going to have the derivative of x, which is 1 times 12 minus 2x squared plus x times the derivative of all of this. So we can say 12 minus 2x squared prime. Okay? And this is chain rule, right? We see a function inside of a function. So we will differentiate with respect to this function. So we're going to have to do, we bring that 2 out and then do this to the power of 2 minus 1. And then we do the derivative of the function inside. So we're going to have negative 2. So let's write now what we're doing. 12 minus 2x squared plus x times, well, we can bring that 2 out, right? 2x 12 minus 2x to the power of 1. Right, we're just bringing that 2 out, and then we have 2 minus 1. And then this is multiplied by the derivative of what's in the inside. Derivative of a constant is going to be 0, and the derivative of x is 1. So we're going to have negative 2. And I'm actually going to put that in the front here. We're going to have plus 2 times negative 2, so negative 4x times all of that. Okay, and this is going to be our derivative, and we have to set this equal to 0. And, oops, there's a really fun way to kind of think about this, and this is going to be factoring. So we're going to set this equal to 0, right? And we have two factors of the same thing. You can even think of this as, say, a is equal to 12 minus 2x. And if you think of this as, actually, no, that would get a little bit confusing. Let's keep it, relatively simple. We're going to say that 12 minus 2x is common to both of them, so we can say that this is 12 minus 2x times 12 minus 2x minus 4x times 12 minus 2x. Alright? And then, using factoring by grouping, we know that these are two common factors, so we can factor that 12 minus 2x out. And so we'll have 12 minus 2x minus 4x. So with this 12 minus 2x times 12 minus 6x, we can set both of these factors equal to 0, right? So that if we have a product of two of these like expressions, and the product of this expression equals 0, then this has to equal 0, so if you multiply this by this, you get 0, and this has to equal 0, so if you multiply this by this, you get 0. So 12 minus 2x equals 0, and 12 minus 6x equals 0. Okay, so we plug in x equals 2, well, we can add 6x to both sides, then you have 6x equals 12, then you divide both sides by 6, so you get x equals 2, and then similarly we add 2x to that side, 12 equals 2x, which means that x will equal 6. Okay, and now we need to, well, we could plug both of these values in. We do need to make sure, well, let's just make sure that these are relative maxes or minimums. So let's do the second derivative test, which again proves to be rather promising. We have, wait, I forgot the actual function. Oh, we can do it again. So We said that if you bring that 2 out and do the derivative of the inside, you get negative 2. So you have negative 2 times 2, which is negative 4, times 12 minus 2x is the derivative of that first expression. And then we said same thing for here. You bring that 2 out. So you have negative 4x minus 12, times 12 minus 2x, I'm pretty sure. And from here you can, let's see if that's correct. You take out the 2, negative 4. Yeah, okay, this seems fine. And so let's do the derivative of this. It'll be a product rule again. So we have derivative of the first times the second. We're going to have negative 4 times the 12 minus 2x plus the second, plus the first times the second, or the derivative of the second. So the derivative of the second will be negative 2, as we've said. So you bring that out, you'll have plus 8x. Okay? So if we plug in x equals 2, we get x equals 2. We will get negative 4, so we'll have negative 4 times 8, and then negative 4 times 8. So let's see, negative 32 minus 32 plus 16. I'm not sure if I'm doing this correctly. I think there's something going wrong here, but negative 48, we still have a relative relative maximum, because we have a f double prime that is less than 0, which means we have a concave down, which means that that horizontal tangent will be equal to, will be a relative maximum. I seem to be losing my train of thought. And let's do the same thing for x equals 6. Wait, what was the formula? I forget. Let's look back at that for a second. We have negative 4 times 12 minus 2x. If x equals 6, then this will equal 0. If x equals 6, this will equal 0, and this will equal 0. So, yeah, we will have incorrect, bounds. And then if you plug in 6 for here, we will get just positive 48. Which means that, so I don't think we made a mistake, actually. When we do, we have a concave up, because f double prime, that's supposed to be f double prime, by the way, f double prime is greater than 0 for x equals 6, which means that the horizontal tangent at x equals 6 will be a relative minimum, as we've said. And that means that the only relative max on this entire interval is going to be x equals 2. And I'm just now realizing, if our function is 12 minus 2x squared, and we multiply by x, if x equals 6, then you just get 0, and we can't have a 0 volume. So, probably didn't need to do any of that. But let's look at f of 2. So we know that x equals 2 will be a relative maximum, right? So if we plug in x equals 2, we'll have 2 times 12 minus 2 times 2. So we're going to have squared. That's the most important part. We have 2 times 12 minus 4, so 8 squared, which will be 64, which is going to be 128. That will be 128 cubic inches, I believe. And that will be the maximum area. Again, just to review what we've been doing, we expressed what the information that we've been given as a function, and then we do the derivative, set it equal to 0, and find the horizontal tangents, and then do the second derivative test to see if it's concave up, which would make it a relative minimum, or concave down. Concave up, concave up or concave down to see if it is a relative minimum or a relative maximum for that horizontal tangent. And then, do whatever needs to be done accordingly, like calculate or, whatever. But honestly, related rates is not as bad as it might seem. Okay, we have only a couple more. I think I might do some challenge questions that I saw a little while ago. We have find the point on the graph y equals square root of x plus 1 find the point that is closest to 3, 0. Alright, so first we need to start with what relationship we can observe. We know we're trying to find the minimum distance, right? So we're going to have to use our distance formula, the square root of y2 minus y1 squared plus x2 minus x1. And this isn't really a proof because I would have to prove Pythagorean theorem for that. But if you've ever wondered why this is, you can think of this as x1, y1, and then say this is x2, y2. This is obviously a line, but you can also draw this as the hypotenuse of a right triangle, right? And if this point is also x2, y1, then this length is going to be y2 minus y1, and then this length is going to be x2 minus x1. And so this distance squared, so let's call this distance. This distance squared is equal to x2 minus x1 squared and y2 minus y1 squared. So when you square root that, you get the actual distance, and yeah, I would need to prove Pythagorean theorem for that, but I think I've already proven that. So yeah, if we have y2 minus y1 squared plus x2 minus x1, let me rewrite this. Y2 minus y1. I keep writing it with not nearly enough space. Hold on. Y2 minus y1 squared plus x2 minus x1 squared. Okay, and so we have y equals square root of x plus 1, right? And then we have some value, 3 and 0. Okay, so if y is equal to square root of x plus 1, then we can say that this is the square root of x plus 1 minus 0, so just this, squared plus x2 minus x1. So this will be just x, right? The input of this one. We can even write this point out. If you have a point x, y, then if y is equal to root x plus 1, then this point is going to be x root x plus 1. Right, so we did y2, or root x plus 1, minus y1, so 0, squared, plus x2, which is going to be x, minus x1, which is going to be 3 squared. So when we do this, we'll get the square root of, the square root of x plus 1 squared is going to be x plus 1. And then we have plus x squared minus 6x plus 9. That's going to be how we will, expand this. And from here, we have y is going to be equal to, well, let's combine all of like terms. Y is going to be equal to x squared minus 6x plus x, so minus 5x, plus 9 plus 1, so plus 10, all to the power of 1/2, because this is a square root. And now we can continue doing what we've been doing with with optimization problems. So far we have some type of relationship between 2 points, and so we can do dy dx. Right? And so we bring that out. This is going to be chain rule, right? We see a function, we get a function, so we bring that out, and then we do minus 1/2. So we're going to have 1/2 times this. Let's not get into square roots just yet. Let's keep it strictly exponent form. We have 1/2 times x squared minus 5x plus 10 to the power of negative 1/2 times the derivative of the inside. So n equals 2, we can bring that out. We'll have 2x, and then derivative of x is again 1, 2x minus 5. And so this is going to be 1 half. We can write all of this under the same thing. We'll have 1 over 2 root x squared minus 5x plus 10. Well, we can even put that 2x minus 5 up there. And now when will this equal 0? This cannot equal 0. This denominator cannot equal 0 because you can't divide by 0. So let's put a can't divide by 0. So this is the only thing that will equal 0, right? The numerator is what's going to equal 0. So we're going to have 2x minus 5 is equal to 0, so x equals 5 halves. And just to be sure, let's do the second derivative test. That promises to be interesting for this one. So, derivative of the first times the second. So we're going to have 1 half. Well, we can bring this negative 1 half out here, so we get a negative 1/4. Negative 1/4. And then x squared minus 5x plus 10 times 2x minus 5 squared. All right, and then this will be negative 3 over 2, I think. And then plus, it's going to be minus, minus 1 half times x squared minus 5x plus 10 times the derivative of that, which is just going to be 2 again. Derivative of x is 1, so just going to be left with 2. And then 2 times 1 half is just going to be 1. Okay, so again, we could plug in values all willy-nilly, but I think it's probably a little bit better if we just plug in 5 halves into here, get 0, so we don't have to worry about this part, and we look at this part. So 5 halves will be 25/4 when you square it, which is like 6 1/4, and then minus 25 halves, so 6 1/4 minus like 12 1/2, so negative 6 1/2, and let's see, maybe I should use a calculator for this. Hold on. We're trying to find the point that is closest, okay? So let's see. Okay. Interesting. I think we've done something wrong. Let's work backwards, see what we could have done wrong. Okay, I think I recognize where we did something wrong. I think some of the people watching this are like screaming at their screens right now because I missed something fairly obvious, I think. I'm pretty sure I did. Let's see. So, when we did the square root of x plus 1 squared, square root of that squared, so we're just going to be left with x plus 1. And then we did minus x minus 3 squared, but we had x plus 1 minus x squared plus 6x minus 9, right? Because we had to do minus x minus 3 squared. Okay, here we go. That's what I did wrong. So we have negative x squared plus 5x minus 8. Let's see if that works. Maybe I should show a little bit more work. We have y2 minus y1. So x plus 1 minus 0 squared minus x2 minus x1. So x minus 3 squared. And then this is x squared minus 6x plus 9. We have to do a minus of all of this. So x plus 1, x plus, wait, what? I think we're going further. away. So negative x squared. Something with the signs. Negative x squared plus 7x. And then 1 minus 9. I think this is going to be negative 8. At the very least, regardless of what this is, I know that this is negative x squared, which means that I'm going to have negative over here, and then all of this needs to be brought down. Okay. Let's, I'm not going to, take this out because, we all make mistakes. I've made several mistakes on this channel, and, you know, for the more, fundamental errors that I think I've made, I do tend to edit that out because I don't want to confuse anybody. But for math errors and this kind of stuff, I'm pretty okay with being wrong. It's a good thing, and it gives you opportunity to grow. So square root of x plus 1 squared minus x minus 3 squared. So negative x squared plus 6x minus 9, x plus 1. I think it is 7x minus 8. So we're going to have negative x squared, square root of negative x squared, plus 7x minus 8. So we can make this negative x squared plus 7x minus 8 to the power of 1/2. Right, and let's see if this works. I was thinking that since this is an odd power, this is like negative 1 to the power of 1, square root of that. Oh, wait, no, that's just I. Sorry, it is rather late. Well, not late, but I am somewhat tired. So we have y is equal to this, right? And then we have to do the derivative. So we still pull out that 1/2. Y prime is going to equal 1/2. Okay, this looks like it'll be quite the complex derivative. Okay, so we have 1/2 times negative x squared plus 7x minus 8 to the power of 1/2 times the derivative of the inside. So still negative 2x. As we said, n equals 2, so we bring that out. 2 minus 1 is 1. Negative 2x plus 7. Okay, so we can write all of this as, I'm going to bring that 7 in front of that negative 2x, so it looks a little bit nicer. We have 7 minus 2x over square root of, or 2 times the square root of negative x squared plus 7x minus 8. And now we can do another derivative. I think we can use quotient rule this time just to really get some practice in. Y prime prime is equal to derivative of the top, which will be negative 2 times the bottom. So we can write this as negative 4, right? Negative 4 root, okay, hold on. Oh, wait, no. Yeah, I'm really losing it. 2 is not part of the derivative, right? This is just 1/2 times all of this. So 1/2 is a constant, does not get included. We have 7 minus 2x, that derivative. Derivative of a 7 is going to be 0, derivative of a constant 0, and then derivative of x is 1, so we have negative 2 times root x squared, or negative x squared, plus 7x minus 8, minus the second derivative, so 7 minus 2x times the derivative of the bottom, which we said was going to be, if this is negative x squared plus 7x minus 8 to the power of 1/2, we said we'd be bringing that out to the derivative of this, which we again said was 7 minus 2x, and then this will be negative 1/2, 1/2 minus 1/2, right? So we have 7 minus 2x squared over, and again, since we brought that 1/2 out, we can put this back in the denominator. Square root of negative x squared plus 7x minus 8 all over, 2 times negative x squared plus 7x minus 8. Right, so now what do we have? Well, let's try and visualize kind of what's going on. Right, so we have a common-ish denominator between this and this. So we're gonna split this into two fractions. Let's put this in parentheses. I know I didn't write this workout the best, but we can split this into two fractions. This will be the numerator of one fraction and another fraction. So we'll have negative 2 square root of x squared negative x squared plus 7x minus 8. So if we divide both the numerator and the denominator by square root of negative x squared plus 7x minus 8 so that we get just one number in the numerator, then this 2 and this 2 will cancel out, so we'll have negative 1 over square root of negative x squared plus 7x minus 8. Again, I know I'm not really showing my work. I should, but I do want to keep this y prime on this because I'm definitely going to forget. But yeah, we can split, this is one numerator and this is another numerator, right? So we split this into two, and then we have this numerator divided by the square root of that negative x squared plus 7x minus 8, and then this divided by the square root of negative x squared plus 7x minus 8, so that you just get square root of negative x squared plus 7x minus 8 in the denominator. And from here, we have 7 minus 2x squared, so let's write this as maybe minus 7 minus 2x squared over, well, this 2 and this 2, they combine, so we have 4, and let's see what this would look like. 4, if this is the square root squared, so this is like 1/2 to the power of 2 or something, then you can add this 1/2 to this 1/2, or no, this 2 to this 1/2, and then you can write this as a cubed. Oh, we can write this as the same power to the 3/2. So this is like the square root squared. So if we write this in terms of the square root, then this will still be squared times 1/2. So square. Wait, what? No, that doesn't make sense. No, so when we multiply, we have to bring this part down, right? Since we are dividing a fraction by a fraction, we have to bring that denominator down. And so when we multiply negative x squared plus 7x minus 8 by the square root of negative x squared plus 7x minus 8, it's the same as saying negative x squared plus 7x minus 8 to the power of 3/2, right? It's the square root times the square root times the square root, so square root cubed even. But the reason that I split it like this is so that when we plug in 7 minus 2x equals 0, let's do that one real quick. X equals 2 over 7, right? When you bring that equals 0, bring that out. You have 2x equals 7, divide both sides by 7, you get x equals 2 over 7. And then from here, this whole thing will just completely cancel out. And from here, we can plug negative 2 over 7 in here. I think it'll be like 4 over 49, which is a relatively small number. And then you add 2. Okay. Wait. Let's see. I don't know. Okay, wait. I might need to do some more research on whether I got this question right or not. But at the very least, I know that if 2 over 7 is a valid input, then we have a negative and a 1. So this f double prime should be less than 0, which means that we do have a relative maximum, right, at that horizontal. So yeah, maybe I should plug it in and see what we actually get, but I'm scared. I'm not sure if I messed up some calculation, but I do need to look back at my work at a later time. But the principle's still the same. We have to um, see if we have a second, if we have a first derivative that equals 0, and we did, we had 2 over 7, and so we set that to, maybe this could, no, but this denominator cannot equal 0, because you can't divide by 0. So 7 minus 2x is the only thing that can equal 0, which means that if x equals 2 over 7, maybe I did some type of differentiation error, or maybe even this is completely wrong, but at the very least know that second derivative should be negative, which means that we do have a relative maximum at x equals 2 over 7. And I don't feel super confident in actually calculating what that thing is, so we're just going to kind of brush that under the rug and kind of go past it. I know that's unsatisfactory, but you know, I'm just a kid. You know, I don't know what I'm doing, but that's kind of weird. Maybe I set that problem up, but weirdly. But I'm pretty sure I did okay. Like everything made sense at least. I thought it did, but something might have gone wrong just in how I calculated it. But the differentiation was pretty good, and that's what is most important. And we have which points on, well, let's just go to the second. We have which points on the graph y equals x squared plus 2 is closest to 5, 0. Okay, this one seems a little bit more complex, even though it might seem slightly easier because we're not working with the square root. So we have the square root of x2 minus x1, so we're going to have, or y2 minus y1, we'll say x squared plus 2, x squared plus 2 minus 0, so x squared plus 2 squared, let's see, wait, was it supposed to be plus? Wait, what did I do wrong? Huh, no, because distance formulas, it's the hypotenuse of that right triangle. No, I really messed something up then. Yeah, no, I'll figure out what I did wrong with that one. But we can do this one correctly. At least I hope we can. Let's do distance formula. So y2 minus y1 squared plus, it is plus, I know that much, because it is the hypotenuse of that right triangle. So, yeah, I don't know, we did two derivatives, maybe I did the first, like, not first derivative, but the first, like, function, that derivative, I think I might have done incorrectly, but we were trying to maximize that, and it wouldn't have made sense to just give us a question that didn't make any sense. So, yeah, no, something must have gone wrong with me. But, you know, whatever. It's not the correct attitude to have, but, you know, we'll figure it out. X minus 5 squared. Alright. Okay, and so we have x to the power of 4. Whoa, don't know what happened. Down there we have x to the power of 4 plus 4x squared plus 4 plus x squared plus or minus 10x plus 25. Okay? And then when we do everything, we have, wait. Oh, no. Maybe I did everything right because, oh, yeah, no. You want the distance to be at a minimum. That's when distance is close. Oh, man, I really don't know. I messed that up so much. I probably should edit that, but, yeah, no, that was a fatal misunderstanding on my part of the actual question itself. Huh. Well, you know, it's whatever. It is somewhat late, at least for me, so I'm gonna chalk it up to that, but, yeah, that's not good. Yeah. When we want the point to be as close as possible, we want the distance between this point, or whatever we get, to be as close to 0 as possible, right? We want it to be a minimum. So, yeah, we want the distance to be minimum. Yeah, I don't know why I was trying to force it to be a maximum. It was definitely not minus. I think our first derivative was fine, but I just plugged something in wrong, and we went on this huge tangent, completely wrong. But you live and you learn. Might need to do another video on that, revisit that one specifically. But we can do this one while we're at it. We have x to the power of 4 plus 5x squared minus 10x plus 25. Okay, so this is obviously a lot. Right? And so this is the square root of all that. And so this is also going to be, as we are referring to it, this power to the power of 1/2. So we can bring that 1/2 out using power rule. N is equal to 1/2. I'll keep this in my brain. We know how well that's working so far. 5x squared plus minus 10x plus 25. To the power of 1/2, of course. So we bring that 1/2 out. We have the derivative of the function with respect to the function. We see a function inside of a function, so we're going to use chain rule. So we have to differentiate with respect to this inside function. So we treat the inside function as if it's just an input. X to the power of 4 plus 5x squared minus 10x plus 25 to the power of negative 1/2, right? 1/2 minus 1 times the derivative of the inside, power rule, n equals 4. Bring that out. And then 4 times x to the 4 minus 1, so 3. And then plus n equals 2, we bring that out. 5 times 2 is 10. Times x to the 2 minus 1, which is 1. And then minus derivative of x we said was 1, minus 10. Okay? And all of these are multiples of 2, so I'm just gonna, for simplicity's sake, cancel out all of these so that we have a nice and round denominator. And so we will have a 2x cubed plus 5x minus 5 all over the square root of x to the power of 4 plus 5x squared minus 10x plus 25. Okay, and now from here we need to see when this equals 0, right? So 2x cubed plus 5x minus 5 equals 0. And for this one, you might need to use a calculator. There might be a way to do this. Let's see. I'll try to calculate it real quick. 5 equals 5. Yeah, no. Let me check your calculator if there is a nice, easy way for this to go. Two x cubed. So, 2x cubed. Okay. 1 second. Alright. X is going to be equal to 0.797. There might be some way to calculate this. I mean, there's definitely some way to calculate this. This is probably some type of a cube root or square root of something very simple. But, we're lazy and dumb and we don't know how to do anything, so we're just going to keep going. We have x equals 0.797, and we need to make sure that this is a relative minimum because I don't know what I'm doing. As a teacher or whatever I'm supposed to be, I have just no clue what I'm doing. So let's go back to what we have. We have to take the derivative of this, the second derivative, so that we can make sure that this is a relative minimum, right? If the second derivative is greater than 0, then our graph will be concave up, or the graph of this, no, the graph of the function will be concave up, so then you can say that the slope of the tangent line is constantly decreasing, or increasing, sorry. Again, still don't know, because it'll go very negative, and then slowly but surely eventually become positive until, it's actually positive and this forms a parabola. So, yeah, we need to make sure that our graph is concave up. So, let's see. We have to do quotient rule, right? Derivative of the top times bottom minus the top times derivative of the bottom all over the bottom squared. Okay, so let's do the derivative of the top. We have n equals 3, we can bring that out. Derivative of x is going to be 1, derivative of a constant is 0, so we'll have 6x plus 5 times square root of x to the power 4 plus 5x squared minus 10x plus 25. And now we subtract the first term, so negative 2x cubed plus 5x minus 5 times square root of, well, not square root just yet. We have to do the derivative of this. Right, so this is the same function to the power of 1/2. We bring that 1/2 out as we did last time, and then we do negative 1, so 1/2 minus 1. That'll be negative 1/2, and then do the derivative of this, 4x cubed plus 10x minus 10, just what we did last time. And then we were able to cancel out the 2. So we got, what do we get? If I remember correctly, we got some 2x cubed plus 5x minus 5 over x to the power of 4 plus 5x squared minus 10x plus 25 to the power of 1/2. After we canceled out the 2's with that 4x cubed plus 10x minus 10. And also, this should be 6x squared. Okay? And then we multiplied all of that. So I think by the end of it, we should just have 2x cubed plus 5x minus 5 times 2x cubed plus 5x minus 5 because we cancel out the 2. So we'll have that squared all over, I just think square root of x to the power of 4 plus 5x squared minus 10x plus 25 seems fine, unless I'm doing something wrong. And yeah, all of this over square root squared. So let's just say all of it under or over x to the power of 4 plus 5x squared minus 10x plus 25. Okay, we could simplify this. We could simplify this a lot, most likely, but it would be, let's say, prohibitively annoying. So let's do this on a calculator. We had x equals 0.797, and bear with me. This is going to take quite a bit of time to actually input. Oh man, I should actually use a real calculator. I think I lost mine, but yeah, that would make it a lot easier. But I could use my phone. We live in the 21st century for some reason, I think. Okay, wait. I can click calculator. Okay. Hold on. 6 times 797. Okay. 6.797 square plus 5 at times square root of 0.797 to the power of 4. Not sure my poor phone can handle all this. To the power of 4 plus 5 times 0.797 squared. Oops, plus 5. Okay. Yeah, no, I'm not good at inputting this properly. Plus 5x squared minus 10 times 0.797. And no, this is riveting commentary. Plus 25. And then plus I think that's it. I don't know. All right, minus so many parentheses. Yeah, I'm just gonna pray to every deity that I know that this is positive. 2 times 0.97 cubed. Oh, wait. This is rather annoying. 197 to the power of 3. Plus 5 times wait. I'm just gonna estimate from here actually. So 0.797. We'll just say that this is close to 1. It's obviously, not 1. There's quite a bit of difference, but 25 is going to be significantly larger than negative 10 times 0.797. Right, and then these two numbers are positive, and if this number is slightly more less negative than 25, then everything on this denominator will be positive. And from what I see so far, this is greater than that, so, well, this is greater than all of this together. So this should be positive, the numerator. And, we can even try and think of this. So if we had 2 plus 7 minus 5, obviously that's not how it's working, but this number should be positive. And, yeah. Oh, well, even if it's not positive, we will square it. And then you will divide it by a number, so that should be a relatively small number. I know I'm just kind of making stuff up, but this is 1, this is 1. Again, same logic. This, whatever this is evaluating to, will not have as much of an effect. This will also not have as much of an effect because 0.797 is a fraction. This might have an effect, but if we just kind of think of this as negative 10 times, like, well, this is 0.8 essentially, then you'll only get negative 8 plus 25. And if this is positive and this is positive and this is only minus 8 plus 25, then they should be positive in the denominator and they should be positive in the numerator, which means that f double prime, because this is starting to get a little bit annoying to input, f double prime should be greater than 0, which means we have a concave up graph, which means that we have a relative minimum, which means that the value x equals 0.797 should be the best point to get as close to 50 as we can. Okay, so let's input that. 0.797 squared plus 2. Again, my phone is not the best for this, but we'll say that's good enough. Again, I probably need to do a better video in the future, just only talking about optimization of those point lines, but I think just in general, I think this was a relatively okay video series, We did talk about first derivative and second derivative tests. We talked about particle motion, related rates a little bit, um, optimization, basic derivative proofs. So I feel like we did get through a good amount of content, but yeah, this definitely needs a revision and one in the near future. But I'm not going to be deleting any of this. It's important to see me make mistakes. I'm not like better than anybody, and I'm also still young, and I got a lot more math out there to math. So I'm pretty okay with doing some dumb things from time to time. But yeah, you know, that's the end of this episode. As I said before, listen to Sometimes I Might Be Introvert by Little Sims. Took me a while to come up with that recommendation, but it is very, very good. Honestly, like, it's up there with some of the most perfect albums that I've personally listened to over the past, like, couple of years. That's definitely a modern, I wouldn't say masterpiece, but well, it's not because I don't think it has the quality of potentially being a masterpiece, but only because, you know, masterpiece takes time. But it's definitely a good album, and there are worse albums that are worthy of that title. So maybe in some time we can see in the past and be like, that was a masterpiece of an album. But at the very least, at the very very least, we can say that this was a very good effort. Production's on point, rapping's on point, everything's on point. It's not even just rapping. All of the features, even though they are few and far between, they are, stellar. And she actually busts out some vocal chops, like actual singing from time to time, and that's a particularly special treat. But yeah, that was some 4.5 hours of derivatives. I know it's not like 4.5 hours straight like it was in integrals, but I watched my integrals video back. Not all of it, thank God, but I just skipped to the end and I was like, oh my God, I sound so miserable. Um, I do like integrals, okay? Like, I like integrals because it's kind of like a puzzle, and it gives me some practice in differentiation, ironically, because I usually try to differentiate them in my head after I integrate just to make sure that I was okay, and usually I do pretty fine. But yeah, that was some 4.5 hours of derivatives. No, it was broken up. First time was not my fault. Second time, so this time, that was my fault. I was tired. But yeah, so that was derivative. I said that several times, but I feel weird not, closing on my normal closer because I already closed on the last part of this. So, bye.